So the next chunk of work is evaluating results. So we're kind of like leaving some of the core math behind, some of the core concepts. There's a lot more to learn. I have only introduced like some parts, like these are things you're most likely to run into as some of the hyperparameters in your model, like momentum is a hyperparameter, learning rate is a hyperparameter. If you have an estimator in gradient boosting, that would be a hyperparameter that you're actually adding to your system. There are a lot of different, so these are things that you sort of pre-add to the model which help it to converge. So that's the way to think about it, a hyperparameter. So the difference between a parameter and a hyperparameter is a parameter gets adjusted along the way. A hyperparameter is a set of initial estimates for all the different parameters of your model. So that goes into the sort of architecture of your model. And that will eventually, and you could get it right or you can get it wrong. And the problem is that your hyperparameter space is huge. It's so there are a lot of hyperparameters out there, and a lot of different hyperparameters, possible hyperparameters for a model. And searching for the right hyperparameter is a very tough problem, and that's why machine learning is oftentimes seen as more of an art than a science, because the challenge is that. And so one of the things that AI Studio uses is something called spectral optimization, which is was introduced relatively late in 2017, and it's something that AI Studio is starting to use. It's probably one of the most advanced ways right now for doing hyperparameter optimization, and it does way better than humans. There've been kind of studies that show that. So I'll show you how to use. So we offer like multiple hyperparameter optimization methods depending upon. The problem with spectral is that it takes a lot longer. So I would recommend using spectral if you're not getting a good answer the other way, and then use spectral, and spectral will get you a better answer, but it takes longer. So, okay, so basically what you're doing is, so you're evaluating the, we're looking at the, evaluating the results of the training. So how do you know whether your model is good or not? And so there are several things that can happen. Your model can be overfitted. It can be biased. And when you talk about bias, you're talking about statistical bias, which means how close are you to the real value. And it can also, or it can have a low overall accuracy. There are many other things that can happen, but those are sort of the three broad buckets of things that can go wrong with your model. There are other things which we're going to talk about, like when you actually test your model. One of the mistakes that people make is just stopping at the validation data and saying, okay, I've got a model and I'm ready to go. You actually have to test the model in the wild, and it could be that either there's a mismatch in terms of how the data is curated in the wild, in which case, as we talked about earlier, you need to figure out a standard automated way of curating the data. Or it could be that there really is a problem in terms of your training set. Your training set does not match reality, which can often happen. And I gave you an example where the training set, every time there's a picture of a horse, there's a copyright symbol, and the AI kind of ended up picking that out as a feature of a horse. So, which means that was a defining feature of a horse. And so when you fed a picture without a copyright symbol, then it wasn't a horse, clearly. So, so that's kind of, so when you have, and that's kind of one of the challenges. It's like you need to know that your training data matches reality. So that's why machine learning is not so trivial. Even though AI Studio massively simplifies a large part of it, it doesn't completely like absolve you of responsibility, because it's all, the model that you're getting is only as good as your training data. And it'll give you the best possible model given your training data, but if your training data is poor, then you can't really expect any results. So evaluating accuracy is not really always so obvious. So classification accuracy is obviously determining how well your model can predict a specific outcome from a set of outcomes. And regression is basically more or less measures the distance from the actual output. And the way to think about it is I mean, like I said, they're variants of each other. Classification is, it's basically it's a discrete, so regression is a continuous form of a classification model. And so in some sense, the concepts are the same, but the measures are a bit different. So couple of things so overall guidelines, validation accuracy is more important than accuracy of the training data. So that's something to think about. Overall accuracy of the model, so if you have high accuracy of the training data but low accuracy of the validation data, then you're probably overfitted. If you have low accuracy over both, then you're underfitted. And if there's a strong discrepancy between accuracy over training and validation data, there's possibly an overfitting issue. So both could be high, but if there's a very strong difference between the two of them, there could be a problem there. But I'm going to go into a lot more detail with this. So if the model is learning, then obviously the validation loss should decrease with the number of epochs. And the decrease should be relatively uniform. If it's a very random kind of jump, that means there's an issue in terms of it's not really learning that efficiently. And sometimes people will say, hey, you know what, for this particular epoch, it was really, like I managed to get high accuracy. That doesn't necessarily say it's a good model, because if it's jumping all over the place, that means it's not really converging. The second thing is you could have there are issues like not enough data. There's not enough signal in the data, which means, for example, so I was working on one training set where a human couldn't differentiate one from the other, but they were supposed to be different because it was a makeup expert that said that this was different from the other. The AI couldn't tell the difference, so you trained it on the model, there's no difference, which probably tells me that the makeup artist was bullshitting, but it's like, so which is, because there wasn't that much of a difference. So which means that, so understanding whether there's a signal there is tough. And with images, it's not as difficult. When you deal with numerical data, it can be extremely difficult in terms of trying to understand relationships between things. An example of that would be if you're doing time series analysis on the stock market. It looks like you got a signal because over time it's increasing, but there's actually should be no signal there. And the reason is quite simply that once you make it into a stationary model, so in other words, you subtract out the increase overall over time, then it's a random walk and there's no signal there. So understanding whether there's a signal in something or not sometimes requires a little bit of a domain level understanding. So the other thing is, so things like resolution can impact how strong a signal there is. If you do a convolutional neural network and you reduce the size of the images to a really small image size, you could be losing enough detail that it no longer is able to pick up the differences. Typically, when you train a network, you can't train on a megabyte-sized image, simply because that's you don't have enough memory on the system. And so you reduce the size of the images to something more manageable. But if there's a ton of detail that it needs to pick up, like in medical imaging and so on, when you go to like a 32 by 32 image, then you're not going to get a good response. So you go to something like 128 by 128 or something like that, but there you still might not get results because you might still lose accuracy. So the challenge, though, is that, of course, you run into memory issues in your machine. Then the other thing is then the model could be learning about features that are not relevant. So it's not really, so this goes back to the copyright side. So it's not overfitting. It's not an overfitting problem because it's not memorizing the data. What it is doing, though, is it's honing in on a specific feature that is not really relevant. And so identifying, so that's why it's, once you start with an overall feature set, and you try and reduce that feature set as much as possible so that you can eliminate things that might just be extraneous to your problem. So the other thing is train with a balanced data set. So if you have, I mean, if you have a general population of like pets, 70% dogs and 30% cats, it's a made-up number. I have no idea. I personally like dogs, so I'm going to bias my model in terms of dogs. So what you should do though is that even though you have this discrepancy, you should still balance it by 50% dogs and 50% cats. And the reason is otherwise your model tends to recognize one relatively well and recognize the other one really poorly. The testing data, however, should go back to the 70% dogs and 30% cats because because that should again reflect reality. So your validation data will be on this, and will give you a really good answer. But your testing will have to be on this kind of population dynamic, and that can result in some very strange discrepancies. Visualization of the original data is very important. So for numerical data, graph it. It's like you should see what it looks like. And there are a lot of things you can do to make it easier to see. Like, for example, there are visualization techniques like PCA, K-means, a lot of things like that, which help you see if there are any patterns in there. And obviously, if you have images, sometimes just open up the images, or if you have audio files, listen to the audio, because that'll kind of like tell you a little bit about kind of what to do. So one case could be so if there's like noise at the beginning, noise at the end, then one way to potentially do this is to build a model that recognizes noise and then eliminate those parts of the overall audio file, which could maybe get you a better result. So that's one possibility. Or just you want to say beginning and end are noise, and then you can eliminate that. So the issue is also the accuracy of the data. And one of the challenges is getting highly accurate training data. Getting a model that's more accurate than the training data is not that's not possible. So if your training data is really poor, there's really not much you can do in order to compensate for that. So the ground truth needs to be there. What you can do is you can compensate for a lot of stuff. You can compensate for low volumes of data. You can compensate for things where you may not necessarily have all the features in place, and so on, through things like gradient boosting or like adding momentum. There are things like one-shot learning. There are a lot of different techniques that you can use to do that. But if your data is not accurate, you're kind of screwed. Then, of course, is the accuracy good enough? It's not always feasible to get an extremely highly accurate model, and it's not necessary because you have to do an ROI cost, because getting a highly accurate model can be incredibly expensive. So if you do, for example, the sentiment model, which that will be an example that we're going to show shortly, using sentiment, the world's record is about 94% accuracy, but you require a lot of compute power and very complex algorithms to be able to do that. AI Studio, if you just put it in full auto, not even in spectral, just full auto in normal mode, you get to about 89% accuracy. So it'll build a model so the question then you have to ask, is that extra 5% worth anything? Using AI Studio with MNIST data, we can get to about 99.1% accuracy. The world's record is 99.4% accuracy. So the question then becomes, is it really worth spending the extra compute power and kind of effort to be able to get there? And there's some problems where we actually outstrip humans, but there are cases where, yeah, we may fall short, but then the question that you have to ask is like, what's the ROI of getting that extra couple of percentage points? And so that's one thing. So you basically need to set some standards, so have something in mind. Like, are you happy with something simply being better than random? In the financial markets, maybe that's all you care about, because better than random already gives you an advantage in the market. If you talk about medical stuff, you probably just need to be better than human. So if I build a model in a hospital, so for a PET CT scan, the average doctor for this particular problem gets it right about 72% of the time, and the model that's generated 74%. Sure, it's not really super high, but it's still better than the average doctor. So unless your hospital can afford to always buy the top, like get the top physicians around the world, it's probably 74% accuracy is good. So it's a business decision ultimately. But one of the things people fall into the trap of is that they say, hey, you know, I want a super accurate model, and I'm going to pay whatever it takes to kind of get me the extra couple of percentages, which is kind of bogus. So the other thing to remember is neural networks are all about probability of outcomes. So you never get there are cases where it can fall into so if you look at this, for example, you notice that it doesn't add up to 1. And the reason is very simple, because in this case it can belong to more than one category. So there are a couple of cases where you can say it can only belong to one category, or there are cases where you can say it can belong to multiple categories. And so depending upon that, your loss function should also represent that. And finally, also look at false positives and false negatives.